Today we will talk on permeability of soils. Permeability is defined as the property of a porous material. So basically, for permeability, material has to be porous, and this porous material permits the passage or seepage of water or other fluid through its interconnecting voids. So voids are to be interconnected for the seepage of the fluid. So basically there are two requirements for material being porous or permeable. One is it should be porous, two it should permit the passage of the water or other fluid through its continuous interconnecting voids. And then such a material having continuous voids is called permeable material. And we also know from the grain size analysis, grain size distribution, also we had just discussed earlier, and as the grain size reduces, permeability also decreases. So it means that gravels or sands, they are highly permeable soils, while silts and clays are having less permeability. So basically you will see that clays are having least permeability and gravels highest, or uh, sands have higher permeability than silts and clays. If you see the example that we use such things in daily life and in engineering also, and suppose rainwater harvesting arrangements is there, then we have smaller size particles of sand on the top, then followed by aggregates of larger size, and then for the larger size. It is because whatever other materials or clay silt is available, that will be basically filtered through the sand, and then we'll have good quality water, and that will be going in underground water table. Similarly, in earth dam, clay is used for the core, because we don't want that water should uh, filter through it. So we have clay which has least permeability in the core, and outside we have for protection also materials which is having higher permeability. Similarly, in canals, you might have seen that we don't want water to get seepage through, so that's why we use clay. So that's why these characteristics, this characteristic is very important. Now, if you talk about the flow, there are two types of flows. One laminar flow, in which each particle flow or travels along a definite path, and in turbulent flow, it is in irregular and twisting path. You can see the figures in laminar flow, that is traveling a definite path. Turbulent, this is twisting, and irregular path. Irregular path, this is basically laminar flow. This is turbulent flow. Now, importance, so though we have discussed briefly about the permeability, one is settlement, determination of rate of settlement of a saturated composite soil layer, because whenever we design foundation of a building or any other structure, settlement is very important. So then stability analysis, we know that all the slopes should be stable, whether they are on highways or railways or even arc dams or even on the hills when we have the road cuttings. So that analysis to be done. So we are to calculate the seepage to the body of the arc dams in case of arc dams, and in case of slope stability also we are to consider it. Then there may be piping, which we have discussed earlier in one another lecture. So we know that piping may occur below the below the dam or the dam, you can see water can go through from one side to another side, so this must be prevented. So this is also to be calculated. So this is important in that analysis. Even this is important in case of expressways and highways. In case of water, the water table is very high and there is a lot of rain, otherwise it can damage the expressway or highway. Similarly, in slope and you can see in the road, highway and settlement, you can see here in a building, and drainage design also it depends uh, on the permeability. Now, if we talk about the laws of the permeability, Darcy's law is of permeability is very important. And for laminar flow conditions, there are two things important here. For laminar flow, another saturated soil. So for laminar flow condition in a saturated soil, the rate of discharge per unit time, suppose discharge is q, rate of discharge will be uh, q upon a, then it is proportional to hydraulic gradient. Hydraulic gradient we have already discussed. So this will be basically question will come q upon a is proportional to I, or q is proportional to IA, and q can be equated as KIA. So in this case, q upon a we know is velocity, so velocity will become equal to Ki. So this is basically the formula. This is called Darcy's law of permeability. Now V is equal to Ki, then K will become equal to V upon I. Now K is the coefficient of permeability or simply permeability. So it will become equal to 1 if I is equal to 1 or hydraulic gradient is 1. So permeability can be defined as average velocity of flow that will occur through a total cross-sectional area of soil under unit hydraulic gradient. We have kept I is equal to 1. So this will become K is equal to V. Dimensions are same as you can see here of the velocity. And we have already discussed that silt has clay has least permeability, and if we go above, then silt will have more silt. Sand will have further more, and coarse and fine sand, then coarse, medium sand, coarse sand, gravel, and so on. So sands will have higher permeability than silt and clay. Now we can do the discharge and seepage analysis for the seepage velocities. This figure you can see is one reservoir R1 and R2. There is a head of H1 here, there is a head of H2 here. The difference of head H1 and H2 is suppose H, and suppose this is soil sample where BB is written, and this is water flowing from here AA and CC to here. So basically the discharge, you will see that one, that this is that earlier as we have discussed, that this Darcy law means this is for saturated soil, so soil will be saturated. And then quantity of flow, because this difference is basically for the flow of water, this head H is responsible. So there is no change in volume of voids and soil is saturated, then the quantity of flow from the cross section AA or BB or CC will be same. So we can say that QAA is equal to QBB is equal to QCC. Now, if we assume, if we are saying that this given condition, this are QA is equal to QBB or is equal to QCC, and we know the soil can be divided in two parts, one soil solids and another void space. Then area available for flow of water is only through the voids, and suppose the area of voids is AV, and suppose V is the velocity of flow voids or seepage velocity or actual velocity, and V is the average velocity across section or superficial velocity. Then area of voids into Vs will be equal to total area, cross-sectional area into V, or Vs will be A upon AB into V. But then we know, since A upon AB is equal to 1 upon porosity, then it also can be equated as 1 plus E upon E, that is in voids ratio. Then so Vs will be equal to V upon N, or V into 1 plus E upon E, and we know that 1 plus E upon E is always greater than 1. So this Vs is always greater than V. So this is basically what we are using. And according to the velocity of flow through soil mass is directly proportional to hydraulic gradient for laminar flow condition. And for fine grained soil deposits, flow is laminar as it has low permeability. Fine grained soils means like clays and silts and very fine sands, because of the low permeability and hence low velocity of flow. So V is equal to Ki, where I is the hydraulic gradient and K is the coefficient of permeability. So in case of sands and gravels where permeability is high, flow will be laminar up to a certain value of velocity, and this certain value of velocity we find out through Reynolds number. Flow through sands will be laminar and Darcy's law valid so long as Reynolds number expressed in the form is less than or equal to unity. So this formula, gamma W V dA upon theta g is less than or equal to 1, where V is velocity of flow, d is the size of particles, theta is dynamic viscosity. So basically this G depends whether we are considering density or unit weight. So accordingly G will be kept. It is found that limiting value of Reynolds number taken as 1 is very approximate, as its actual value can have wide variation depending upon characteristic size of particles used in it. So if we discuss factors affecting permeability, then there are 10 numbers of factors: size of soil particle, specific surface area of soil particle, and even shape of soil particle, wide ratio, soil structure, degree of saturation, water properties, temperature, absorb water, and organic matter. You see many of these factors are can be equated to other factors, also can be related rather than to other factors. And suppose we are saying size of soil particle, then we know that permeability varies according to size of soil particle. A coarse grained soil which has higher size particle, they have more permeability, and fine grained like fine sand, silts, and clay, they have lower permeability. So we can say that K is proportional to T square. As the size of the dia is less, then it will be K will be less, and size of particle is more, than it will have higher permeability. So this depends on size, and K is proportional to T square. If we talk about specific surface area of particles, then it also affects the permeability. Higher the specific size for surface area, lower will be the permeability. So K will be inversely proportional to the specific surface area. Third is shape of soil particle. Rounded particles will have more permeability than angular shape. It is due to specific surface area of angular particles compared to rounded particles. Wide ratio, if you see, then in general permeability increases with wide ratio, but it is not applicable to all types of soil like clays. But for clays, we can say K is directly proportional to some coefficient, then E cube upon 1 plus E, where E is wide ratio. And for coarse grained soil, this may not be applied, and K is directly proportional to E cube upon 1 plus E. Now, if we talk about the soil structure of any two similar soil masses with same void ratio need not be the same. So it may have, suppose it has soil contains flocculated structure, and particles are at random orientation, and permeability is more, and it contains dispersed structure like in clays, then it will have a less permeability. Degree of saturation and entrapped or entrapped air. Partially saturated soil uh, has basically fully saturated soil has more permeability than partially saturated soils. So it is because partially saturated soil contains air voids which are formed due to entrapped air. This air blocks the flow path and thereby reduces the permeability. Then water properties we talk, then if it is viscous particularly, then it will have less permeability because viscosity decreases, temperature is increased, viscosity decreases, and permeability increases, decrease in viscosity. So viscosity is less than permeability will be high. So it is inversely proportional. It means permeability K will be inversely proportional to 1 upon mu. And then we talk about the temperature, then you know that the temperature as increases, then the viscosity decreases. So it means that the K is inversely proportional to 1 upon mu. It means it is directly proportional to temperature. So temperature affects the permeability in soils. Permeability is inversely proportional to viscosity of the fluid, and it is known that viscosity varies inversely to the temperature. Hence, permeability is directly related to temperature and directly proportional to the temperature. Now, if we talk about the adsorbed water, then we have earlier discussed adsorbed water in one of the lectures. Adsorbed water is the water layer formed around the soil particles. So basically, this reduces the size of void space and permeability reduces or increases. Organic matter also decrease permeability because they block the voids. Also, there may be we can find out permeability and of the stratified soil deposits, because in the site we don't get single type of soil generally. So if there are number of layers or stratified soil is there, then we are to find out the permeability. Two cases can be considered. First one is flow is perpendicular to the bedding planes, and the other one flows parallel to the bedding. You can see here, if we can talk first, let flow perpendicular to the bedding plane. It means you can see there are a number of layers of the soil of thickness h1, h2, h3, and so on, and then hn. V is the velocity in this one, Q is the discharge, and I1, I2, I3, In are the hydraulic gradients, and permeability K1, K2, K3, and so on and Kn. You can see these layers are here, and we are talking about flow perpendicular to layer. So H we can consider equal to H1 plus H2 plus H3 and so on plus Hn. So total head loss will be supposed to be sigma H delta H, then delta H will be equal to delta H1 plus delta H2 plus delta H3 of all the sum of all the layers. Then hydraulic gradient, we know I1 will be equal to delta H1 upon H1, I2 will be delta H2 by H2, delta S, I3 delta H3 by H3, and so on. So this way we can determine the hydraulic. So basically Q is same in all the layers, then area cross section of the same, and velocity is same in all layers. Suppose Kz is the average permeability perpendicular to the bedding plane, and Kz into I will be equal to Ki for first layer Ki1, K1 I1, the second layer equal to K2 I2, and so on. Kn In equal to V. Then Kz into sigma h upon delta h upon h equal to K1 of delta h1 upon h1, and so on until Kn delta h1 upon hn equal to V. So we can substitute, and once we substitute here, then we also know delta h1 is equal to delta h is equal to delta h1 plus h2 and so on. If we keep these value here from here, then Vh is equal to Vh upon Kz is equal to, that is average permeability is equal to Vh1 upon K1 plus Vh2 upon K2 plus and so on Vhn upon Kn. V will get cancelled in all the terms. So Kz will be equal to H upon H1 upon K1 H plus H2 by K2 plus H1 H1 K1. So this will be permeability in case of flow is perpendicular to the bedding. You can also find out flow permeability in case of flow parallel to the bedding plane. These are the bedding plane, and this is the V same V here, then V1, V2, V3, and V and R of different layers. And here I will be same in all the layers, and V will be same in the after here this V and Q. H1, H2, H3, Hn are there. Total height is H, and same velocity V1 flow is Q1, V2, Q2, V3, Q3, and so on. So in this case, we know that V is equal to Ki, that same. So V1 is K1I, V2 is K2I, and so on. Then we can find out Q is equal to Q1 plus Q2 plus Q3 plus Qn, and then Kx into I into H. Ks is the average permeability which we are wanting to find out. So this would be equal to K1 into IH1 plus K2 into IH2 plus KNI HN. I get cancelled, so Kx will be K1 H1 plus K2 H2 plus and so on upon that, where H is equal to H1 plus H2 plus HN. In other words, we can find out Kx, which is permeability of permeability in case of flow parallel to the bed plane, and it is will be, you can see K1 H1 plus K2 H2 plus Kn into upon as it means this is weighted mean value when we consider K1 H1 upon H1 and weight being less of each other. And we'll see that permeability parallel to bedding plane, that is Kx, which has come here, is always greater than permeability perpendicular to the bedding plane Kz, which was discussed earlier before this. So thank you very much. We will have next portion of community next time. Thanks a lot.